All right, so do I have a, let's save this. All right, so last time we wrote these constructors for what an empty environment is, and then an extend-env, which takes in a single variable with its associated value and an existing environment, and it adds to it, right? So you were supposed to rewrite extend-env to allow for multiple variables to be defined within a single scope. Is that right? So instead of single var, this would be a LOVAR, LOVARs, and LOVALs. List of vars, list of vals. Is that what I asked you to do? Something along these lines. Okay. So I guess let's just get this for right now. All right. So right now this guy is a lambda that takes in a. Let's go here. Two lists and an environment that we're extending. So when we extend an environment, we're going to probably create a list containing our new list, well, our list of vars, our list of vals, and the old environment. Is that correct? It's a list of 3 elements. Okay, so we can create a list, low vars, low vals, env. That essentially does what we're asking it to do.
Do you want the variable and the value to be in the same list, though?
Is that what I told you to do? So this is my idea here for what I just did. So I would think maybe AB 57. This is our list of variables. This is our list of the associated values. Here's our environment that we're extending. So let's just start with this. So we're going to build an empty environment and then extend that empty environment with this list of variable names and list of values.
So what should the end result look like? It should be AB.
The list containing the list AB, the list 57, and the empty environment.
Why would you want that empty list at the end, the empty environment?
Because this is your end case to let you know that you're out of stuff to check.
Well, wouldn't you already know that when you get to the end and there's nothing more to grab?
Well, you would, but we're building this in terms of constructors. So we can't extend nothingness. So we're extending the empty environment. Or are you saying we can build the empty environment, so instead of building this as a list like this, we would cons this onto the cons this onto the env?
Yeah, you would just.
So you want to build it this way.
You would just insert it into your empty.
You want to say
so
cons low vars onto the cons of low vals onto env. That'll give you a list that looks like this.
Yes-ish.
Because if you did it the other way, then if you...
Well, either way is acceptable. It just depends on how you write apply-env.
Yeah. No, because if you extended the environment once, added say two name value pairs to it, then if you extended it again, those first name value pairs that you had the first time would be in another list entirely the next time you extend it.
Who?
Like you extend it, you add.
If I do this, so let's just shadow some variables. So here we'll create. Let's do CD, and then 5172. So now I have a list containing 4 lists.
Yes.
See, I don't think I like that implementation. I like that last thing being its own. Yeah.
What I did was I created each time I recursively called extend-env and kept I took the car of the list of each list and put those in a list. And then I cons that onto the recursive call.
Yeah, see,
Yeah.
I mean this
And then
this is a better representation.
Yeah.
Because now I have the most local environment is represented as, well, I have a global environment here It's just a big data structure. The car of it and the catter of it are our variable value pairs for that environment. Once we run out of that, we can get the CADDR, which is our embedded environment. That's the next scope that we can then apply the exact same stuff to. So that guy right there is the same type of animal as this guy right here. Yeah, make sense? I mean, the other way's not wrong. I mean, it'll have implications in how you implement apply-env. So, I don't think I gave you a specified structure of exactly how you write this. I think I maybe suggested that you might do it as kind of a parallel list implementation where you have a list of your variable names and a list of the associated values.
I think it would have been nice to have like an end list, an end result to see what structure, because how I ended up doing it was I had a global environment, and then within that I had multiple scopes that were parallel instead of nested.
And that's fine. I mean, there's nothing wrong with that. That's a perfectly acceptable approach to a variable environment. It just changes the way your apply-env is implemented, which is no big deal, right? So, I mean, as long as your environment has structure and you can search through it, and based on what we're doing in here, you're at least building it in terms of these constructors of empty env and extend-env, that's perfectly acceptable. Potentially even better. I'm not thinking ahead enough to know whether or not yours has some benefits other than this. So I guess let's go this route. Did more people do it like this, or did more people do it as a flat list? So his version of this was my cons one, right? It was
I think the only difference was that the variables were in a list by them. So you had the name value pairs in a list, and then you had a list of those as a scope, and then I had a global environment. That's what I had. So it was three. It ended up being three nested lists with your environment level, then your scope level, and then your variable value pair level.
Okay, so yours did not look like this?
No, it would have had one more list enclosing it.
Enclosing this part?
Yes.
Okay, so that guy would have been inside of a list, and would this guy be inside of a list?
Yes, because
it's
they'd
basically
each be in there.
Sorry, so it's basically a list of scopes inside the
Yes,
scopes.
it's a list. An environment is a list of scopes, and a scope is a list of variable value pairs.
Okay. So that's fine. So if we're going to take this then, if we're going to take in these guys, we're going to build a list out of, so you did this. You said list of low vars, low vals, and then you cons that list onto env. You did that.
Yeah, I just paired, so C and 51 were in their list, and D and 72 were in their list.
Oh, so you merged these already?
Yes.
Okay, so you had you created a single list here. Oh, no, I get it. You had a bunch of variable value pairs.
Yeah.
So this would have been C51, D72
Yes.
in yours. Okay. So your extend-env was more complex, which then allowed your apply-env to be simpler.
Yeah.
Is that a fair statement?
Yeah.
All right. So how many people did this version of it? Just like I have here. Exactly like I have here. You did the merge on this step?
Yeah.
Okay. So then we'll go ahead and we'll
List should just be the car of low val and the car of low bars or whatever, and then you should recursively call it extend-env, right?
But that kind of breaks it, because then that is further extending the environment it's creating a new scope level for each of those guys. Did yours do that?
Sorry?
Did you have a new scope level for, like, was C51 in a more local scope than D72?
No, they were in the same scope.
Okay, so what you did is you had like another function here called, let's say merge lists. And this guy would have been a lambda that takes in a low vars and low vals. And it would have gone through and merged those guys together, right? So we could assume low vars and low vals are the same length for our example.
I think I read the question slightly differently in that I didn't think of taking in a list of variables and a list of values. I just had, you input one pair and then you input the next pair.
Yeah, that's what I did. Is I took extend-env was lambda vlist environment. So it just took in vlist, which was two lists, and the two
I
lists
gotcha. So you passed in this. You passed in C51. This is all inside of a list. So C51 and then a second list of D72.
Yeah, I read.
It's okay.
Multiple
It's okay. So this is your parameter to extend env was a single value followed by an environment, and that single value was a list of two lists, a list of name value pairs.
I passed a variable, a value, and the environment.
Okay, so your guy looked like this. This is extend-env. Do I not have enough closers? Oh, that's because I'm doing this merge list guy up here. So you had define extend env3 to be a, all right, I get it. So you cheated a little bit. To be a, let's just say a list of vars. Well, let's call it list of, well, it would have been a list because you would have passed it in like this. Oh, you did? Okay, hold on. Let me see if I can understand that. So let's do list of pairs, low pairs, and an env. So you took two parameters, right?
I had the variable. I had the variable, the value, and the environment.
A single variable.
A single variable, single value, and the environment. Is how I read the question.
Var, val, env. So the same thing we originally had.
Yes.
Okay.
And then I just wrote supporting functions so that you could expand a single scope.
Oh.
Because that's what.
So
that's
you
how
would
I
call
read the question.
extend-env multiple times,
Yeah,
but it would add things to the exact same scope.
Yeah. So what I ended up having is I had extend environment, which would add another scope. And then I had extend scope, where you could
Oh,
choose
I get it.
which scope you want
I
to
understand.
add the
I understand.
variable value
Okay.
pairs to.
Got it. So you had a secondary constructor.
Yeah.
So you not only had the ability to create an empty environment and extend an environment, environments were really extended with scopes.
Yes.
So you had something called really define empty scope.
Yeah.
And then extend scope.
Yeah.
All right. So let's see. With that in mind, how many people did it that way? We got like 11 different solutions. Okay, that's all right. We'll solve this 11 different times. No big deal. All right. Let's start off with a relatively. This has your idea of a scope built into it. All right. So what I have highlighted there is a single scope. Okay. And this scope, when merged together, finds, we have C is equal to 51, D is equal to 72. They just happen to be, think of them as just being implemented as parallel arrays. Okay, so for the sake of argument right now, let's work with this. Because I think there are some advantages to the way you're doing it from a speed perspective of applying the environment. Because you're already separating stuff into scopes, therefore you don't have to do the merge step every time you're trying to apply. Fair enough. So let's go this route first. And this is good because the important thing is understand that we're each kind of creating our own language here, right? So how you implement your variable environment, I'm not going to say it's unimportant. I mean, you want it to not be horrifically implemented. Like it needs to at least be accurate, right? So you need to be able to store variables. You need to be able to get the values out. But there's more than one way to pull this off. So maybe the way I suggest it, which I think would be fairly consistent with how the book kind of goes down the path. I think the book kind of discusses having an empty environment and wrapping that with a new scope, but they don't call it a scope until later on. Okay, so doesn't really matter. So this is our starting point for our environment, let's say. Okay, so this is maybe how I would have intended for you to do extend-env. So now these two constructors are still pretty simple, right? There's not a whole lot to these. And at this point then, apply, so let's define apply-env, which is a lambda that takes in a var and an environment and should boil down to the value of that var in that environment, or sometimes, like a lot of times, the scheme way of doing things would be return false, boil down to false if something bad happened. All right. So the idea here is that we're going to look for var in an environment that kind of looks like this. All right. So we know that as long as the car of this environment, well, let's ask this. Is the car of every environment a list? Should be. This will be our final environment, right? The empty list. Okay, so we know it's a list. We know the car of env will definitely be a list. We know we're done when the length of that list is 0. Okay, or it's the null list. Okay, so we can throw a cond here. So cond null car env boil down to false. All right, so if we're out of places to search, didn't find the value. Make sense? All right, otherwise, now we got some stuff to do, right? So otherwise, we know that the car of env is going to be something that looks like that, what I have highlighted. Okay, a list of variable names. So what I want to do is I want to go and find in that list of variable names the position. I think I was telling Doctor last night, think of it like Java's index of. Kind of a decent way of thinking about this. So search a list for the position of a variable within it and return either a positive number or -1 if it's not there. So literally implement index of. So for right now, let me just write define index of to be a lambda that takes in a, let's call it a symbol and a list of symbols using our book's notation, if you will. Okay, and what we're going to do is we want to return the index of this guy where it finally exists. So if the car of, well, actually we want to say if list of symbols is null, that means we're out of places to search, right? List of symbols is null, so we're going to say if null, let's do it. Do we want to do it in a cond? Nah. If null list of symbols, if that's true, then we're going to return -1. If we ran out of places to check, return -1. Okay? Now we're going to see a weird stopping place here. So we're following a pattern we've done before. Okay? So we'll return -1. Otherwise, what are we going to do? We're going to look. I do want to do this as a cond. Change my mind. Null list of symbols, return -1 for right now. Otherwise, if it's not a null, we want to see is S equivalent to the car of list of symbols. If that's a true statement, we're going to boil down to a 1. Actually, depending on how we do this, we might want to boil down to a 0. Let's leave it at 0 for right now. we're going to do a mathy problem. This is our mathy add stuff to get an index type thing. Else, we're going to go ahead and add 1 to calling index of on the same symbol and the cooter of list of symbols. All right, so if we're searching for a, and we're going to bump into where our problem is. Our problem deals with the -1 right now. Okay, so if we're trying to search, if we're looking for a D in this list right here, so this is our list of symbols, and we're looking for a D, we're going to come through, we're going to say, is this guy the empty list? He's not. Is the car of this a D? It's not. So we're going to add 1 to calling index of, passing it the same symbol on the cooter of the list. So now we have a list just containing D there. Spin back through. Is this list the empty list? It's not. Is the car of it equal to the symbol we're looking for? It is. Boil down to 0. Okay, so with that in mind, what do we get? We'll get a 1. So plus 1, 0 will give us 1. The D is at index 1 of that list. Make sense? Because we're going to be using this later on with list ref. List ref gives us a value at a particular index. Now, let's say we were looking for an F in here. Okay, so we didn't find the D yet. Okay, so now we're going to come to this. We're going to say else add 1 to the index of the rest of this stuff, which is going to be the empty list. It's going to spin back up. Are we dealing with the empty list? Yes. So what are we going to do? Are we safe returning -1? Well, just look. We're not dealing with environments right here. We're just dealing with a function called index of that searches a list of symbols for S.
Well, it won't boil down to -1 because you're adding 1 and then calling it.
So it's going to add 1 plus -1. Correct? Okay. So what do we need this to boil down to? Say this again. What is n? That's an excellent question. So when in doubt, invent variables, right? So what do we want this to boil down to if we're solving for index of?
Could you just, on the way back up, check to see if the previous call is returning a -1, and then just keep on passing the -1 up.
The previous call, so
So like the first question on asking also as well as null, ask if it's -1. If it's -1, then return -1.
ask if what is -1.
No, you'd have to do it where you're adding instead of where you're adding index of. You'd have to somehow split it to check if index of is returning. If index of is returning a -1, you would have to just instead of adding, you just return -1 instead.
So you want to throw an if in here?
Yes.
Okay. Well, it might be more complicated than it has to be.
I don't know why you don't just make it instead of returning -1, it returns false.
Okay, well, so we can do that. So we already said -1 might be problematic, so you want it to return false. That's going to break this math real quick. 1 plus 1 plus false.
Yeah, that's the issue I ran into the last time I tried to return false in a function. So that's where I got my if statement for the addition from. I just said if it's returning false, just return false and don't try adding.
Okay, well, how do we do this? Is this a 2-star problem? Index of? Shouldn't be. Doesn't it seem like a pretty straightforward type problem? What do you think? How can we solve this?
small.
Not that you know of.
You use a let to hold the value.
Hmm?
You use a let to hold the value, and then change that if it ever gets to -1, then.
You could potentially use a local let environment here.
We could pass the position we're at and index out to.
Well, let me ask you this. Do we have to do an addition type solution here? Potentially, we could use maybe zeros and ones. Places where it's found or not found. What if I did this? Let's back up here. What if I said cons a 0 onto whatever index of returns, passing it S and the cooter of LOS?
So then at the end you just take the length of the list.
Just con 0 onto it. So when I get to here, what's happening? So right now I'm just boiled down to 0. When I do find it, what do I want to do? How about cons 1 onto index of S cooter of LOS? So maybe I do that in the event that I found it. So I have a bunch of zeros, then a 1. Finally, what do I do here? If I ran out of crap to search for, I want to put 0 on there? Maybe the list 0? Boil down to the list 0? So now what do we have in the end? In our list CD, what would my code ultimately look like? I'd have something that looks like not found, found, like that, right? If I was looking for the D. If I was looking for not found and, well, if I was looking for F, let's say, that means not found, and that last one's going to give us another 0. How did we know that this was not found? It was not found when I ran out of places to check. What about when it was found? If I found the D. The D says, put a 1 there, cons it on to whatever's returned by index of on the cooter of it, which is then going to give me a 0. So this is a situation where it was found. What if I didn't cons it on? What if I just returned the list containing a 1?
That's the most helpful definition, though.
Well, not dealing with scopes, just dealing with index of. So if I just return the list 1 here, hello. Oh, Dr. Racket, free advertisement. All right, so why would anybody want to click that? It's such a stupid place to put that. So if I'm looking for a D, this is going to give me, I'm building a list, so I'm consing a 0 onto whatever index of is for the next one, and then I'm returning a 1. Now we're done. Right? Did we finish? I looked. I found that it was not there, it was not the C, so I cons the 0 onto whatever index of is for the next guy. Then I found it in my second position if I was searching for a D. So now I have just the list 1, so my final output will be that. Correct?
Switched. Okay, so see where it says if it's null
Mm-hmm.
or no when it's
Not when it's null.
Will I ever get to the null thing here? So follow this for a second. Will I ever get to this production? Never recursively call it. So if I am looking for a D in this list of symbols, wouldn't my result be this? I know I found, so leave it at that for a second. What if I was looking for an F in my list of symbols? It would look like that, correct? How do I know when I found something? The last element is a 1. How do I know when I didn't find something? Last element's a 0. Specifically, where did I find it if the last element was a 1? Well, not dealing with environments, just dealing with index of. This is the only guy that exists in our entire world right now. How did you figure out position 1?
Well, don't you have to go through the list and
My last element of the list is a 1. What index in that list did I find the value I was looking for?
because there's two numbers and it starts at 0.
The length of the list minus 1. The length of my resulting list minus 1. Make sense? So if this guy ultimately is going to boil down to a list, and that list is either going to have a, how do I get the last element of the list and find out if it's a 1?
Isn't there a, didn't you show us the reverse list
Yeah,
thing?
you can get a reverse. Okay, so you can get a reverse, and reverse will flip the list around. Then we can take the car of the reverse. Say, is that a 1? If it is, then I want to return the length of that list minus 1. Make sense? So would I do a let environment here? Surely index of can't be this difficult. Got another suggestion? We just solved it, right? We solved it in a way that seems like it would be more difficult than it should be. Doesn't index of sound like it's a fairly easy thing? Are we just searching through a list? It might be. But unfortunately, we don't have access to that.
Can you pass it like index of, like pass it the position you're at the moment, and then add 1 to that every time until you find it. And then if you don't find it, it just returns a 0. I mean, or not necessarily a 0, but it's not there.
Okay.
It's -1.
Does anything say that our index of couldn't take in a current pos? Can't we have a third parameter there? And maybe when we first call it, we pass in a 0?
So couldn't you just start it off at 0 instead of putting pause?
So then down here, what do? We just call index of.
No, because you call it recursively.
Yeah, but,
We call index of, passing it the same symbol. Index of, passing it the same symbol, the coder of our list of symbols, and plus curpos 1. My list is 1 shorter, but now curpos is a 1. When I finally find it, just boil down to curpos. Otherwise, boil down to -1. So if I'm looking for the C here, first time I call index of, curpos is 0. it'll boil down to value of curpos, 0. That's the correct position of it. If I'm looking for the D, I don't find it initially, so I'm in the else. So I just call index of, passing it same symbol, passing it one shorter of a list, and adding 1 to curpos. So curpos is now 1. Notice I'm not building up this giant summation in this last recursive call. Instead, I'm just passing in a 1 as another parameter. So now I come in here and says, is the symbol I'm looking for equal to the D? It is. Boil down to 1. If I was looking for an F, then I'm going to call curpos again, passing it curpos, or call index of again, passing the same symbol. The rest of our list, which is going to be the empty list this time around, curpos is now 2. If I ran out of crap to check, return -1. Make sense? Question for you. So, do you recognize this as an accurate solution? Does the solution work? Why didn't we come up with this first?
It requires the user to pass in a 0, which is kind of unnecessary.
No, the user's not going to be calling this. This is our own little helper method. You're right. I mean, it's a harder to use function, so that's one possibility. Okay. Probably not what I was necessarily thinking of. So I've been harping on this idea of looking for patterns, right? And our go-to pattern in our head is always compartmentalized into certain things. Like, okay, well, we're looking for null lists. Are we building up a list here? Or are we building up a sum? Well, now we have another pattern. Sometimes you don't want to do recursive math because you can't back off. Okay, so tail recursion sometimes messes us up. In this case, when we get to the very end and we need to completely change our value, we have a new pattern now because we don't want our final answer to be based on a recursive call to a whole bunch of answers. So we really went down a bad path because of an old pattern when really we've introduced a new pattern. Make sense? Okay, so it's okay for us to have multiple parameters, extra parameters, if you will, coming into your helper function. You know, I would agree with Alex when he says that, well, if the user was calling this, we probably want to make it as idiot-proof as possible. So you might wrap index of, you might have something called index of helper, which calls index of starting with a 0, something like that. But this solution, now that we see it, isn't so horrible. All right, so now for apply-env, we can use this index of. If my environment is the empty list, that means I've looked everywhere in all the scopes and didn't find anything. Okay. Otherwise, I know the car of my env here will be a list of variable names. Okay, it'll be something like this. All right. So what I want to do is we're going to ask the question. Let's go ahead and call upon this guy first. So I'm going to say we're going to call index of, passing it the variable, passing it the car of env, and passing it a 0. That call right there is going to boil down to either a -1 or a real position. If it's not equal to a -1, so we can do, what do I want to wrap it as? Let's say if it's greater than -1. If whatever index of returns is greater than a -1, that means it was found. Correct? And if it was found, we should boil down to the same position inside of that guy as our whatever's returned by index of. So we're going to boil down to list ref. Does it take the list first and then the index, or take the index and the list? I think list then index. We'll find out pretty quick. So list ref of the car of the cooter of our env That's going to be this guy right here, right? The first element of the cooter of our environment will give me that list. Specifically, I want the value that lives at that position in there. I'll kick this down a line for us. So if I found it, that's what this line says, if I found it in my local environment, the local scope, if I found the variable name in the local scope, return the value from the local scope. That's what that guy says. Else, do what? We want to call apply-env. Passing it the same var and passing it the actual environment. That means everything that's not this, that's not this. So if I take the cooter, I'm left with the list containing this. If I take another cooter, I'm left with the list containing this. If I take the car of that, I'm left with my next environment. The CADDR. CADDR of env. That will extract that last environment. Okay, so now let's just go ahead and let me do a define env to be this guy. Just so I have it in a variable. So now I should be able to type env and get that list. Okay. So now let's call apply-env. Passing it, let's look for a C in env. And we should get the 51, the value of variable C. Similarly, apply-env, passing it the D, I get the 72. Apply-env, passing it the A, I get the 5. Apply-env, passing it the B, I get the 7. Apply-env, passing it an F. This fails because I do not have a car in my env. What does that mean? As I broke this down, let me print out env again. I checked this local scope. And then what did I do? I said, give me the next scope. That is the car of the cooter. So it'll extract that guy. All right. Then I looked for the F in this guy. Didn't find it. So I extracted the car of the cooter of that guy. Did I find a car in there? So I don't want to say the car of env. I just want to say, is the env false? Or is the env empty? Okay. What I got returned by the car of the cooter was that last environment, not a list containing the empty list, which is what you were trying to avoid, or what you thought we maybe were going down that path, right? All right, so now I should be able to search for an F in here, and it should give me a false. Didn't find an F. And I should still be able to look for my other guys, 5 and those guys. All right, that makes some sense? How that guy worked? So the difficulty in this one, so we're going to say apply-env doesn't look too bad there. So our complexity there was this guy right here, which says, search the list of variables in my current scope for the current guy I'm interested in. That's the difficulty. Is the variable that I'm looking for somewhere in my current scope? That's our search. We're going to have to do that no matter what implementation we're using. I don't care if we're using Amish's version of this implementation or, let's see, Dover, you had a little bit different one, right? Okay, and then there was probably 3 or 4 other weird bastardized versions of this variable environment. Doesn't matter which of those representations we have. Okay, it doesn't matter what our data structure looks like when we're working with our variable environments. Any way you cut it, we're going to have to search through that guy looking for the variable that we're interested in. Okay, you did a recursive search through where you had to keep basically taking something off the stack or something, taking your variable value pair and looking at the car of it over and over and over again. Is the car what I'm interested in? If it is, return the catter. Over and over and over again until you finally landed on your the correct answer or you ran out of crap to check. One of the two. Okay? So apply-env really won't matter. It really won't matter if you, any way you cut it, you're going to have to write your version of index of. We can easily just replace the word index of with search. The word search. That's what we're doing with this, right? Because of the way I wrote my code, I decided to represent my variables and values as separate lists. Parallel arrays, parallel lists type of implementation. So I'm searching the first guy for the position of the variable name. Once I find it, I grab that same value from the value in that same position from that guy. Okay? In Amish's version, what's he doing? He's not looking for a position. He's dealing directly with pairs. So he has a thing that looks like this, 51, and another thing that looks like this. So he's going to look at the car of this guy and say, is that the variable I'm looking for? If yes, return the catter. If not, let's look at the next guy. Is this the car of this guy the guy I'm looking for? If yes, return the catter. So on and so forth. Still doing a search. Okay? Let's see, what other representation did we have? So let's go that route. So yours was, you took in a, oh, that's right, you broke it into scopes, correct? Okay. So let's trash all this. So you created something called an empty scope. And this is a lamb that takes in no parameters and returns the empty list. So an empty scope is kind of a synonym for empty env.
Yeah.
Okay? But we'll still call it empty scope because we want to think about it like that. All right. And then you have a, extend scope?
Yeah.
I already like this implementation, by the way. I like how it's broken into constructors. So we have extend scope. And this guy's going to take in a var val and a scope.
Yes, and then I had to also pass in a int for location, because what ended up happening is you're extending a particular scope, of which there can be multiple in the environment, because the environment was a list of scopes.
Okay.
So
let me keep going with this. I want to see if I see the same need for that.
All right.
So for right now, so what you did here is scope is already a list of variable value pairs.
Yes.
So what you did here is you consed the list of var val onto scope.
Yes.
Okay,
Yeah,
so that's
a scope is a list of two lists.
list of two lists. Okay, fair enough. So that's what extend scope does, right?
Yeah.
Okay. So now what you did is to create the thing we had down here, we had define env to be a, let's see. Oh wait, hold on, we need to change extend-env. So extend-env takes in a scope and an environment to add to it, right?
Yeah.
All right. So what we'll do here so extend-env is going to, well, let's just start with our empty env here at the very end. And then I'm going to add to this guy. Just going to cut this for right now. So we're going to say we want a extend scope, passing it a and 5, along with the empty scope, like that. So that extends our scope 1 level, right? Then I'm going to, this is a scope in and of itself. So then I'll do extend scope B7 onto that scope. So there's a scope. And then we'll extend env with, this is going to get scary quick. Okay, we're going to extend env with this scope and the empty env. Okay, I'm going to steal this again. So now we're going to extend env with an extend scope what did I have? C was like 51 or something like that. D was 72. Is that right? All right. Onto the environment. So that's into this guy. So onto. Okay. So extend env onto the environment returned by extending env with that scope onto the empty env. All right, so that's your env. Oh, it doesn't like this anymore. It's okay. Your extend env is going to take a scope and cons it onto the env. Okay. All right, so that is your environment?
Yes.
Okay. So this is a scope. So this was one variable value pair added, and then we extended that scope with this guy. So when we extend scopes, we ultimately build a object known as a scope in your world. And here's a second scope. Okay. Our first scope is our most local scope, let's say. Okay. Fair enough. So now we need to write apply-env in terms of this scope. All right. Now we would probably say that this seems to be a little bit of a complex representation of an environment, but that doesn't mean it's bad. Okay. In fact, once we write apply-env, we might find that this is easier to work with. Okay. So we're going to write define apply-env. And this guy is going to take in a lambda, var, and an environment. All right, and the type of thing we're looking at is this type of thing, right? So once we're left with the empty list, we know we're out of places to check. So we have the same cond there. So cond null env return false. Otherwise, we want to search in a scope for our variable. Search in an individual scope. So what we're going to do is we're going to have another function here. Define apply scope. And this guy is going to take in a lambda, var, and a scope. Okay. And this guy is going to have a cond. Null scope return false. Otherwise, a scope is a list of two lists. So we want to look at the car of that to see if it matches our guy. So EQV car of scope. If that guy is the same thing as var, then we're going to get the CADAR, the catter of the scope. That'll be our value, and we're done. Otherwise, we're going to call apply scope on with the same var and the cdr of scope. So that's apply scope. Apply-env then says if we still have scopes in our environment, then we can say apply scope it's going to be a little redundant, but whatever. We'll write this the way we know how to write it right now.
Yeah, I actually wrote apply-env.
Okay.
I didn't even bother with apply scope.
Oh. Well, the way I have apply scope, you didn't write apply scope is what you're saying. Okay. I think this is going to be more appropriate for our data structure version of it, but let's write it and see if you agree. All right, so we're going to say apply scope, and we're going to, so if we have a scope to search, we're going to search for the variable in the car of env, which is going to be our scope. All right. Now the issue here is that this guy is going to boil down to either a value or a false, right? Well, so I want to say if it's not false, so if this guy boils down to something other than false, actually what happens? If this would say if not false, this boils down to false. So if this boils down to false, then what am I going to do? I'm going to call apply-env on the passing it the var and passing it the cdr of env. That is the environment with everything but the first scope in it. Else, we know we had our answer, so a little redundant here. We'll call apply scope. So that would be apply-env in terms of those scopes. So we checked the scope, made sure, and I think this should work, because technically our scope is really sort of kind of a predicate. It returns false if the value wasn't found, and returns something else if it was. So I'm asking, does it return false? That's what this not thing does. Then if it does return false, we're going to check the next scope using apply-env to check the next scope. Otherwise, we'll just go ahead. We know we found our answer. We'll return apply scope of that guy. All right. So where's my else not allowed? Up there. Poorly written. Oh, because this isn't a cons. That's a cond. Should be a little happier with that now. Okay. So there's our env craziness. So we'll do apply-env. We're going to look for a passing it our env. That does not work. So really we want to say if not number. Well, here, let's actually, why use the not if we don't need it? So we're going to say if this guy's a number, let me steal this. Let me steal this. I'm just going to rewrite it. I'm not going to steal it. All right, so if that guy's a number, then we're going to call apply scope on it. So do the exact same thing we just did, knowing that it's an actual value. Okay? That's where a little let would come in fairly handy. Else, we'll call apply-env, passing it the same var and the cdr of env. Okay, so we'll call apply-env, passing it a, and passing it env, we get our 5. apply-env passing it b in our environment, we get our 7. Apply-env passing it c in our environment, we get our 51. Our d, I can't edit that one. He's already fired. Our d in our environment, and we get a 72. And finally, let's look for an f in our environment, and we get a false. Okay, so now you said that because you didn't write apply scope, you ended up needing to keep track of an extra value inside of extend scope?
No, the reason I had an extra value inside of extend scope is in case you wanted to add a value to, say, the second scope in your environment.
Oh, I see.
Yeah.
So you allow somebody to...
It was purely just for adding it after
Yeah.
that.
Gotcha. So you allow somebody to go back in and tack on an extra variable to a scope from 3 levels ago.
Yeah.
Something like that. Okay. Trying to think from a language theory perspective, would that be something you ever have to do? Because typically scopes live and die in a self-contained environment. So, but I get it. Yeah, I mean, it's not uninteresting. So I'm trying to think if there's an advantage to that. So imagine, so for some of you where this stuff is already rotted through your soul and you're kind of like, where the hell am I? What's going on? So imagine, let's bring this back down to earth a little bit. So imagine a programming language now, just any old language, where we define variables. And we're down here in a different part of our program, and we want to add something to a previous scope.
Add a value or add something?
Add a variable. Add a variable, not change a value. Add a value. So let's see. Out of curiosity, let's see if Java supports this. So this would be one scope. Then we hit this, and that's going to be another scope. And this is kind of bypassing any understanding we have of compilers. Static int b is equal to 7. Now what I want to know is, can I say system.out.println b? I can. Okay, so it'll run. So I never printed out A, but here's my B and there's my 7. All right, so this is more of a compiler's thing. So this is a 2-pass compiler where it actually ran through initially and built up all the symbols in the global scope. So it created the global scope, added this value to it, then added this value to it. All right, then it added this function header to the global scope because this guy lives within the scope of driver. This scope inside here was not actually created until this guy was called. So in Java, it wouldn't need to support going back and adding things to a later, to an earlier scope, even though it seems like it maybe would. So I'm trying to think, is there an example of a situation in a language where this would be helpful?
Probably not.
Well, I don't know. I guess I wouldn't throw it out too fast. I mean, we consider, our languages consider to, continue to evolve, right? I like using the word evolve, but Dr. Locklear doesn't like the word evolve, as it applies to programming languages. Yeah, I mean, it doesn't seem to break. It's not like we're saying it's not intelligent design. We are. So, is it the wrong word?
No. It's just a different definition.
So he's just wrong. This is on record. Yeah, so I'm just thinking, might a future programming language benefit from having the ability to add or remove things from previous scopes?
don't know if you're already doing something similar with the compiler, like how Java's doing it. I don't know if there'd be a situation.
Well, I'm kind of thinking about, let's say you have the global scope is where this is most obvious. So we have stuff happening at the global level in our program. And let's say that we're in a function call that's using some global variables, and let's just say that there's a conditional in here that says the user pressed yes instead of no. Because they pressed no, a certain thing from our global scope is no longer a thing. I mean, might it be beneficial to be able to legitimately remove it from our scope? I mean, because from that point forward, it's not going to be used. Therefore, it would be, especially if whatever the thing is big. I mean, that could be memory inefficient. Similarly, what if they say yes here, and now all of a sudden we need a variable at the global level that might be used this point forward that wasn't so instead of having to create a whole bunch of variables for a whole bunch of just in cases, we could arbitrarily add variables to the global scope as needed if after a decision was made, we say from this point forward, it may be relied upon for that variable to be there. So at that level, it sounds like, okay, it might be helpful. Problem is now is the compiler, from a compiler design perspective. If we're going to go through and we're going to read all that stuff, we can't so let's say we have a function down here that as humans, we know we won't call unless the user said yes up here, okay? And this function utilizes a global variable that is not defined. But we know as humans that it will be defined before it gets here because we added it to our scope here. Kind of make sense? So while it might make our program more memory efficient, it's going to make our compiler significantly more complex to write.
You have to check every single time it found a global variable that isn't defined. It would have to check if the only way you can get there is through defining the.
Well, but you might have to augment the language then. So kind of like what Swift has done for the some of you who are in the Apple Watch class. Swift has these things called optionals. So what you might have is a special syntax for maybe variables. Like here's the variable, it might be in play during runtime, but it might not. Just kind of let this one slide. So a directive to the compiler letting it know that I'm using a variable and treat this as if it exists. Treat it as if it exists. That becomes more complex though than in strongly typed languages, because now how do you treat it as if it exists if it doesn't have a type associated with it? So the syntax, the maybe syntax might also have to define the type. I mean, this might be a really inconvenient language. I'm just saying it's not completely without merit. I guess at the end of the day, it comes down to whether the juice is worth the squeeze type thing. Yeah, I guess interesting. But I would say in our modern languages, adding things to previous scopes is probably not all that helpful. But I understand why you wrote it that way. That's not wrong. It's just maybe more powerful than it needs to be. Okay, so that's apply. So let's see. Which of these implementations do you like better? The first one that I wrote or Amish's version? I like this version better.
I think now that I'm looking at it, I'd probably want to do something with actually nesting some of the scopes because it's more obvious with to have local scopes and progressively local scopes with a nested list instead of having them all side by side.
Okay, possibly. But keep in mind, most people are not going to be looking at this representation of your scope. This is purely for our internal logics. And the reason why I kind of like your implementation here is if we look ahead to our lambda calculus expressions, you know, and as Nick pointed out, I think last class or the class before, our current lambda calculus expression only has one identifier. But clearly our functions in real life can have 0 or more parameters, right? So as we bump into these guys, as we define variables that aren't necessarily, don't have values bound to them yet, but your solution here with the extend scope makes a whole lot of sense, because now we don't have to do extra crap. For each of those elements in our list, in our identifier list, we can just extend scope. You know, we'll create an empty scope here, and then for each one, extend that scope with this guy and default value. Extend scope with this guy and default value, so on and so forth. So it actually will be pretty convenient for walking through a list of 0 or more variables inside that scope, because we'll get a base of empty scope. It is a scope. There's just nothing in it. Empty scope. And then if we have 2 things in it, we'll extend that empty scope twice, giving us our 2 things. So this is going to be pretty convenient for that implementation. So even though it's maybe a little bit more, you know, robust, if you will, in terms of actual data representation, so we can almost think of this as being kind of like, you know, kind of like XML, right? So it's a pretty verbose, you know, representation of our data. What comes with that is the ability to maybe work with it in a fairly friendly manner. I don't know that apply-env and apply-scope are very scary here, are they? I mean, the only tricky part here is, you know, how many A's with the car and the catter, that kind of stuff. You know, how to extract the exact little value. But if you drew out a list, you could kind of figure that out, right?
It's worse on my screen.
Oh. Is it?
Yeah, I did a couple things that are fairly dense and not
Fairly dense.
not,
I like that phrase.
yeah.
Go ahead.
I was going to ask, what's the difference between EQ question mark and EQV question mark?
So EQ question mark. Have I not done EQV? So we have we have 4 different things. We have equals, we have EQ question mark, we have EQV question mark, and then we have equal question mark. So without going too deep into it right now, we can say that we can always use equal. Equal's never wrong. Okay? But equal like tests bone structure. Actually, is it fair to say equal's never wrong? Maybe. That might be fair. But possibly not. So EQ question mark will compare things like symbols, numbers, but not... Trying to think what EQ would do, but EQV would not. I think there's only one thing. I think they're almost identical. Let me try something here. EQ A, EQV, A. Well, those are identical there.
What is it? Why is it saying false there?
Because these are not the same. This list and this list, even though they look the same to us, have different pointers. It's comparing their values. Yeah, not the contents of. But actually, I don't think equal, does that do that? Is it question mark? Yeah, that'll look at the contents of the list. So equal is, but there is a difference between EQ and EQV. There's like one example where it works but doesn't work on the other one. Let me just Google it here real quick. Scheme EQ versus EQV. All right, well, we've seen the equals just for our primitive types. All right, well, in any case, I'll keep looking this up, but no homework for next class, but definitely go back and review this video. It's like, oh my God. Okay, definitely review this video. We did some fairly heady stuff here today. We'll probably have a quiz next class dealing with something. I obviously won't have you write something this deep, but dealing with some concept from class today. Okay? So definitely study it. Let's see if I can get an answer for you.